We often hear that modern physics is close to a final theory of everything, that the remaining problems are technical details, that with a bit more data and a bit more computing power, the deepest mysteries of the universe will fall into place. That picture is comforting. It is also wrong. In this video, we're going to look at a long conversation between Brian Greene and Edward Witten, a conversation that quietly dismantles that illusion. Edward Witten is widely regarded as the most influential theoretical physicist alive today, and the only physicist ever awarded the Fields Medal, the highest honor in mathematics. When someone like Witten speaks openly about what physics still does not understand, we should pay attention. I watched the entire interview, so you don't have to. My goal here is not to summarize everything that was said, but to explain what you actually learned from it, about gravity, quantum mechanics, string theory, and the limits of scientific explanation itself. If you care about how science really progresses and where its deepest problems still lie, stay with me until the end. The conversation begins by looking backward. In 1986, when string theory was controversial and widely doubted, Witten made a prediction. He said that 50 years later, physicists would still be talking about string theory. Nearly 40 years have passed, and he stands by that prediction. But not because string theory has delivered a final theory of nature. String theory did make genuine progress. In its early form, physicists could only study it when quantum effects were small, using approximate methods. In the 1990s, new breakthroughs revealed how the theory behaves when quantum effects become strong. In certain special situations, string theory even provided a mathematically complete description of quantum gravity, something no other approach had achieved. This was not hype. It was real progress. And yet, Witten stresses something crucial. Despite all of this, we still do not know what string theory fundamentally is. We do not know its guiding principles. We do not know why its equations take the form they do. This is not a minor gap. It is the central conceptual problem of the field. To understand why this matters, we need to talk about gravity. Modern physics rests on two pillars. Quantum mechanics describes the microscopic world of particles and fields. General relativity describes gravity, space, and time. Both theories work extraordinarily well, but they refuse to fit together. For more than a century, physicists have tried to reconcile them, and they have repeatedly failed. According to Witten, the reason is not just complexity. It is mathematical incompatibility. Einstein's equations are deeply nonlinear in a way that standard quantum methods cannot handle. The techniques that work for electromagnetism and nuclear forces simply collapse when gravity is involved. String theory survived because it approaches the problem from a different angle. It is more restrictive than ordinary quantum field theory, so restrictive that gravity becomes unavoidable. In fact, string theory was not invented to explain gravity at all. It was originally an attempt to describe the nuclear force, but the mathematics kept producing a massless particle with spin 2. In physics, there is only one possible interpretation of such a particle. It is gravity. String theory does not allow you to decide whether gravity is present. It forces gravity into the theory. That is why physicists could not ignore it, even when they were deeply skeptical. As string theory developed, however, another challenge emerged, one that pushed physics into uncomfortable philosophical territory. The theory does not predict a single universe. It predicts an enormous number of possible universes, each corresponding to a different solution of the equations. Different shapes of extra dimensions lead to different physical laws, different constants, and different cosmic histories. This led to what is known as the anthropic idea. Maybe the universe looks the way it does not because it had to, but because only certain universes can support observers like us. Some features of our universe, such as the extremely small rate of cosmic acceleration, seem almost impossible to explain otherwise. Witten speaks about this with rare honesty. He says the anthropic perspective made him unhappy for years. As a physicist, he wanted explanations, not selections. He wanted to derive the properties of particles and forces from fundamental principles, not accept them as environmental accidents. Eventually, he made peace with the idea, not because he found it satisfying, but because he could see no alternative. As he puts it, the universe was not created for our convenience, or for our understanding. At this point, the conversation turns to one of the most profound discoveries in modern theoretical physics: duality. Duality means that two very different mathematical theories can describe the same physical reality. Each theory looks nothing like the other, each answers different questions, and yet both are correct. The most striking example, discovered in the late 1990s, shows that a conventional quantum field theory with no gravity at all can be exactly equivalent to a universe with gravity, curved space, black holes, and galaxies. A world like ours can emerge from a theory that appears, on the surface, to describe none of those things. This forced physicists to rethink what a theory even is. If multiple, radically different descriptions exist, then none of them can be the final truth. They are languages pointing towards something deeper, something we still do not understand. Dualities are not rare exceptions. They keep appearing in physics and even in pure mathematics, suggesting a hidden structure beneath our current frameworks. The conversation then moves to quantum mechanics itself and to the famous measurement problem. Witten rejects the idea of wave-function collapse as a useful explanation. Instead, he traces the problem to a deeper issue. What does it mean to know something? Early interpretations assumed that observers simply know measurement outcomes without explaining how. Later approaches treated observers as quantum systems, but only shifted the mystery rather than resolving it. Witten's conclusion is subtle and deeply educational. Consciousness, he believes, is an emergent phenomenon, something that arises from complex physical systems like brains. Knowledge is emergent as well. And because the interpretation of quantum mechanics depends on what it means to know something, the interpretation itself may be emergent. We should not expect a perfectly sharp final answer at the deepest level. When asked about free will, Witten offers a calm, matter-of-fact view. Our actions arise from the physical state of our brains, and he sees no contradiction in that. And when asked whether, under such a picture, he truly deserves credit for his discoveries, his response is simple. If he discovers something beautiful, he enjoys it without worrying about it. This interview is not about certainty. It is about intellectual honesty. It shows what it looks like when someone at the very edge of human knowledge admits how much remains unknown. If you found this useful, consider subscribing for more deep dives into the history and foundations of science. And if you want to explore any of these topics, string theory, quantum gravity, or the measurement problem, in more detail, let me know in the comments. Physics is not finished, and that is exactly what makes it interesting.